All right, we're going to take a little deeper look at intervals of increasing and decreasing, and then we're going to use the first derivative test to determine if we do have any relative extrema. So the first thing we're going to do, of course, if judging by what we just read, we probably need to take the derivative. So right here, we're starting with a quadratic function. Taking the derivative, we get 4x. And once we take the derivative, in order to find intervals of increasing and decreasing, we need to think about when could it change from increasing to decreasing or vice versa. And so that's when we find our critical values. And our critical values are when our derivative equals 0 or when our derivative does not exist. So judging by our derivative, it is a linear function. A linear function always exists. So we're simply going to set it equal to 0, and when we solve this, we have one critical value at x equals 0. What that is saying is that our derivative equals 0 right here. A 0 slope is a horizontal tangent, and we know a horizontal tangent is a place where our function could change direction from increasing to decreasing or vice versa. So in order to understand what's going on both sides of this x value, I am going to slap it down on a number line, and I'm going to think about what's going on both sides of that x value of 0. To the left of 0 would be the interval from negative infinity to 0. To the right side would be from 0 to infinity. And what is actually happening over here, whether it's increasing or decreasing, we can think about what would happen using our derivative. For instance, what is left of 0? Well, it's any negative number. Literally any negative number is less than 0. And if you take any negative number and multiply it by 4, you're going to get a negative value. So my derivative is always less than 0 over here. I'll try to keep it different colors. Our derivative is always less than 0 over here. So since the derivative is negative, so our original function, notice we checked our derivative, we saw the derivative is negative over here. So the original function, our original function y is decreasing on this interval from negative infinity to 0. Tying it all together, that's what I see is going on over here. To the right side of 0 would be positive x values. And any positive x value plugged into our derivative is giving us a positive answer. So therefore, over here on this interval, our derivative is positive. And since the derivative is giving us positive outputs, so how does that affect our original function? Our original function, y, is increasing on the interval from 0 to infinity. So again, negative derivative means we have negative slopes. It is literally going down over here to the left of 0. Whereas over here, the derivative is positive. That's positive slopes. It's moving up over here, and we see that visually as increasing. And finally, tying this together, our first derivative test. So our first derivative test, we look for critical values. We look to see if our function changes at that critical value from increasing to decreasing or vice versa. And notice that that value of 0 does give me an actual point on the graph. If I take that 0 and I plug it in to the original function, because remember the original function is real points on the graph, I get the point 0, -6. That point 0, -6, because my function was going down and then it went up, that point right there is where it changes from decreasing to increasing. So we are going to have a relative minimum right here at 0, -6. And that is because my function y changed from decreasing to increasing at x equals 0. All right, let's completely tie it all together. So take a snapshot in your brain of this. We're going to graph it. We're going to see this all play out. All right, let's graph this. Oh dear, what was our function? 2x squared minus 6. 2x squared minus 6. Looking at that original function, and I will just graph this right here on the Zoom 6 standard graph. Notice right here at 0, -6. It changes from decreasing to increasing. It's decreasing over here from -infinity to 0. It's increasing from 0 to infinity. Right there is a relative minimum. So visually, it is checking out. It is checking out visually. All right, let's take a look at another polynomial. We've got x cubed minus 6x squared plus 9x minus 1. Same deal. We're still looking for intervals of increasing and decreasing. And then we're going to take a look at the first derivative test and tie it all together. So, of course, we're going to start with our derivative. Once again, our derivative is resulting in another polynomial. And a polynomial, of course, is always continuous. It's always existing. So when we're looking for critical values, because remember we took our derivative, now we're looking for critical values, it's always existing. So critical values are when it doesn't exist, when the derivative doesn't exist, or when the derivative equals 0. Because it always exists, I'm going to find all critical values that give me a result of 0. I'm going to do that by factoring. It looks like I should be able to factor this one. 3 times 9 is 27. Multiplying to get 27, adding to get -12 is a -3. But you know what? I'm overdoing this. We can factor this one first by just factoring out the 3. So I was thinking I needed to multiply a times c and factor by grouping and stuff, but it is even simpler than that. I can just pull out a 3. So I was making that more difficult than I needed to. The resulting quadratic can be factored even simpler, x minus 3 times x minus 1. And using the zero product property, I can see my solutions are x equals 3 and x equals 1. So we found the two values in which our derivative equals 0. Remember, your derivative equaling 0 means that is where our original function has a horizontal tangent. And if we have a horizontal tangent, you can think about that last graph, our horizontal tangent means we're probably, not always, but probably changing directions from decreasing to increasing or vice versa. So we're taking those values, the x equals 1, the x equals 3. giant number line, so I have plenty of room to play around. Slapping my 1, slapping my 3 on here, and thinking about the intervals. I have an interval from negative infinity to 1, an interval from 1 to 3, and an interval from 3 to infinity. And I'm thinking about what is going on here. Well, over here to the left of negative 1, what does my derivative say? If my derivative is negative over here, well, that means my function will be decreasing. If my derivative is positive over here, my function would be increasing. So I'm going to check a value less than negative 1 to check, a value less than just 1 would be 0. If I plug in 0 into my derivative, notice I get a positive number. And so my derivative over here is positive. And because my derivative is positive, my original function is increasing. My original function was y. Y is increasing on this interval from negative infinity to 1. Take a look at the second interval from 1 to 3. We need to know what our derivative is doing. Do we have positive slopes here? Do we have negative slopes? I'm going to check 2. I'm going to think about 2. 2 is on this interval. If I plug 2 into my derivative, you could think up here, you could think down here. All of these right here are different forms of our derivative. And so if I plug it in down here, it would be a negative 1 times a positive 1 times a positive 3. A negative times a positive gives me a negative. So I see my derivative is negative on this interval. So that tells me that y is decreasing on the interval from 1 to 3. In between 1 and 3, y is decreasing. And finally, from 3 to infinity, check some value, any large positive value you want, you plug it in, and we do get a positive first derivative. Our first derivative is positive, and that tells me my original function is increasing on the interval from 3 to infinity. So I have found my intervals of increasing and decreasing, and I'm now going to tie it together with the first derivative test and get an idea for what these functions look like, or what this function looks like. So right here at 1, at the x value of 1, notice our function y was increasing, and when it got to the x value of 1, it started decreasing. And so because our function goes from increasing to decreasing, at x equals 1, y changes from increasing to decreasing. So, increasing to decreasing, we must have a relative maximum right here. I know it's a relative maximum because that value of 1 actually exists on my original function, and it changed from increasing to decreasing right here. That is the place where it switched and changed directions. 1 actually exists. If I plug it back into the original function, I have 1 minus 6 plus 9 minus 1. Negative 5 plus 9 is 4. Minus 1 is 3. So we have a relative max right here at 1, 3. I got that point. That point had nothing to do with this 3 over here. Let that be known. That 3 has nothing to do with that 3. I got that 3 because that is an actual point. 1 is the actual x value in which it changed direction. So I plugged it back into the original function to figure out when what what point on the graph actually has the x value of 1? And it's that point right there. It's on the actual original function. And so when we pull it up on the graph, we'll see it's that value, it's that point where it actually changes direction. Over here, we see it changes from decreasing to increasing. At x equals 3, y changes from decreasing to increasing. If we put 3 back in the original function, we're going to get an actual value out. We can do that right here. That's 27 minus 54 plus 27 minus 1. That's negative 27 plus 27 is 0 minus 1. That gives me a negative 1. So at the x value of 3, I get out negative 1 because it changed direction from decreasing to increasing. That actual point right there would be a relative minimum because it changed directions at this exact point right here. That point is going to be a relative minimum. Notice it went from decreasing to increasing, so this point down here is lower than most points on the graph. Or it's lower to all the values around it. All right, so here's what we noticed. Intervals of increasing and decreasing, we used them to determine relative extrema, and when we did that, that was the first derivative test. Let's check on our graphing calculator. X cubed minus 6x squared plus 9x minus 1. See if I can remember that. All right, we got x cubed minus 6x squared. Oh no, that doesn't look good. Okay, all right. X cubed minus 6x squared plus 9x minus 1. What do we got? Let's see. Hit and zoom 6, get that standard graph. And, all right, notice. It's increasing. Our function's just increasing, all the way from negative infinity. As we move to the right, it's increasing until we get to that x value right there of 1. And notice right there that point is 1, 3. That is a relative maximum because now it changes direction to decrease until we get right here at the x value of 3. That right there is a relative minimum at 3, negative 1, and then it increases as we continue going to the right. So this is exactly what we had just noticed. It goes from increasing to increasing again with that relative maximum and then that relative minimum.